In this video, we're looking at a rotating disc. It's rotating on a bearing with negligible friction. And there are two additional masses mounted to the top of this disc. Those are connected to light springs. And as the disc is freely rotating, a latch is released and these springs retract, drawing those two masses closer to the center of rotation. Because of conservation of angular momentum, the whole system is going to speed up. And so we're going to work through several questions here. First, looking at the initial and final moment of inertia. Second, computing the final angular speed of the system. And third, finding the increase in kinetic energy for the system. So to do the moment of inertia part, we simply add the moments of inertia for all the different pieces of the system. And in that initial configuration, I have a heavy disk in addition to 2 point masses sitting on the edge of the disk. We have to recall that the formula for the moment of inertia of a disk is 1/2 mr squared. So I initial starts out with a 1/2 mr squared for the disk. Plus we have these 2 point masses, and the formula for the moment of inertia of a point mass is simply mr squared. That's little m in the diagram. R is the same as the radius of the disk itself because these masses are sitting at the very edge, and there's 2 of them, so we need to multiply this term by 2. Now we can plug in the numbers. We're told the disk has a mass of 2.5 kilograms. Its radius is 15 centimeters, and that has to be converted to meters, so that's 0.15 squared. The mass of each of those iron weights is 350 grams, or 0.350 kilograms. And they're sitting at the very edge of the disk again, so that's a radius of 0.15, and we have to square that. And keeping a little extra precision, we get 0.04388 kilogram meters squared for the initial moment of inertia. Now for the final moment of inertia, I know it's going to be less than the initial, because I have more mass concentrated closer to the center of rotation. And all we have to do is adjust for the fact that these iron weights are now at a smaller radius. They're at 8 centimeters from the center. And we'll go ahead and just plug in the numbers right from the start. I have the original disk. It has the same moment of inertia as before. I have 2 of those masses. They still have the same mass of 0.350, but now they have a radius of 0.08 or 8 centimeters. And again, going all the way out to 4 significant digits, I've got 0.03261 kilogram meters squared. Now, as that moment of inertia decreases, the angular speed is going to increase because the total angular momentum needs to be conserved. And that's what we address in part B. I want the final angular speed of the apparatus. Well, the initial angular speed was given to us as a frequency, in other words, rotations per second. And I need to convert that to radians per second so I have the proper units on my final answer. So I have 1.8 rotations per second. I'm going to multiply that by 2 pi radians per rotation. Just doing a little unit analysis here. The rotations cancel and I'll get radians per second. In other words, a proper angular velocity. This gives me 11.31 radians per second for the initial angular velocity. Now we get into the conservation of angular momentum part. We know that L initial is equal to L final. Because there is no external torque acting on the system, that's because the friction in the bearing is negligible. And L is I omega, so I have I initial, omega initial, is equal to I final, omega final. We'll go ahead and solve this symbolically for omega final. And I've used 2 different notations here for omega initial. You could call it omega naught or omega I, it doesn't matter. I go ahead and plug in my moments of inertia, and my initial was 0.04388, my final 0.03261, and my initial angular velocity was 11.31 radians per second. And now I'll go ahead and round off to 3 sig figs. I get a final answer of 15.2 radians per second. Now, one interesting thing about this process is that we know angular momentum must be conserved, but after we run the numbers and get the final angular velocity on the system, we're going to find that the final energy is greater than the initial energy. And that's what we address in part C. We're asked to compute the increase in kinetic energy. So I need to look at K initial. That's 1/2 I omega squared. And we just plug the numbers in. We already have the total moment of inertia. And we have the initial angular velocity. That was 11.31 radians per second. And when we run the numbers on this, we get 2.81 joules. We do the same thing for K final. This time the moment of inertia is less because there's more mass closer to the center of rotation. So 0.03261. And the angular velocity is greater because to conserve angular momentum, as the moment of inertia goes down, the angular velocity goes up. And when we run the numbers on this, we get 3.77 joules. So to find the increase, we take the final minus the initial, or delta K, and we end up with 0.96 joules for the increase in the energy. So one final comment here is that anytime you see a change in energy for a system, there should be some kind of explanation for it. And in this case, our increase in energy is just coming from the retraction of these springs. So there was spring potential energy stored in those. We allowed them to retract at least partially. We don't know whether or not they're at their equilibrium length, but the retraction of a stretched spring is a source of energy, and we have a reasonable explanation for the increase, and we're done with the problem. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.